Hi, I'm Hengda He from Columbia University. Today, I would like to talk about changes in whole brain network connectivity induced by TMS stimulation of the L-DLPFC, a concurrent functional fMRI-EEG-TMS study. I have no disclosures. So in this study, we used the TMS over the left dorsolateral prefrontal cortex, the left DLPFC, as a treatment for depression. And we want to investigate the network level effects of the TMS. And we asked the specific question that what will happen to the relationships between brain networks if we deliver the TMS pulse to the left DLPFC of the brain. For example, we might be wondering what will happen to the functional connectivity between the deformal network and the frontal parietal network if we deliver the TMS pulse. Well, if you look at the literature, there have been some studies that show that if you deliver the single pulse TMS at the node of the central executive network, it's going to introduce a significantly negative effects on the functional connectivity between the central executive network and the deformal network. There have been some other studies as well. They showed that the RTMS treatment is going to introduce a negative effects on the functional connectivity between the subgenual anterior cingulate cortex and the ventromedial prefrontal cortex. And in this study, they also showed that the baseline functional connectivity associated with the subgenual ACC is a predictor of the clinical outcome in the depression patients. So in this study, we want to quantify the TMS-induced changes in the whole brain functional connectivity. And we are also interested in that these functional connectivity changes might be a potential biomarker for the clinical outcome. Well, after we quantified the TMS effects on the functional connectivity between brain networks, another aim of this study is to investigate the dependency of such effects on the brain state. So here we used the EEG prefrontal alpha phase as an index of the brain state. We choose the alpha oscillation because there have been some studies that showed that the timing of the stimulus onset relative to the phase of the EEG alpha oscillation, it has an impact on the perception of the stimulus. Well, these results suggest a gating mechanism of the prefrontal alpha oscillation, which shows that the brain networks associated with the alpha oscillation might have different excitability at a different phase of the each alpha oscillation, and it might have like a different downstream effects on the other brain networks. So as shown here as an example, if we deliver the TMS pulse at a specific phase of the EEG prefrontal alpha oscillation, for example, as shown here, we might observe some moderate induced functional connectivity changes between the brain networks. But what if we deliver the TMS pulse at another phase of the EEG prefrontal alpha oscillation, for example, as shown here? We might observe like a stronger functional connectivity changes between the brain networks. So in this study, we want to investigate such brain state dependency of the TMS-induced effects. So here we used a data set with the concurrent TMS EEG functional MRI. So here we delivered a single pulse TMS at the left DLPFC of depression patients, and we also recorded the EEG signal and the functional MRI, both signal from the brain. So the first analysis that we did is the general linear modeling whole brain analysis, because we want to know that if we deliver the single pulse TMS over the left DLPFC of the brain, which brain networks are going to be activated by the TMS. So here I'm showing the results from the GLM analysis. And then we did the parcellation based on the Schaeffer atlas because we want to quantify the induced response across the brain networks. What we did specifically is the quantify of the percentage of spatial coverage for each brain networks by the TMS-induced response. So here I'm showing the percentage of the spatial coverage, and I'm showing both the medium as well as the lower and upper quartile across the subjects. Well, after we quantified the TMS-induced response on the brain networks, the second question that we want to know is that how the delivery of the TMS pulse is going to change the relationships between the brain networks. So that is the TMS-induced functional connectivity changes between the brain networks. To do this, we use the psychophysiological interaction analysis, which is the PPI analysis. And here, this equation basically describes this PPI analysis. Well, the term that we are interested in is this term. This term is going to model the interaction between the both signal at ROI-A and the timing of the TMS. So the beta waves here is going to represent the TMS-induced functional connectivity changes between the both signal in ROI-A and both signal in ROI-B. So finally, for the brain state dependency analysis of the TMS effects, here we are trying to basically label the TMS trials based on the phase of the prefrontal alpha oscillation. And here we use this phase as an index of brain state. So in this figure, at first I'm showing the timing of the TMS, and at the same time we recorded the EEG signal from the prefrontal electrodes, and from the EEG we get the phase of the prefrontal alpha oscillation, and then we use this phase to label our TMS trials. The TMS trials, they were labeled into 4 phase beams, and for each phase beam we modeled the predicted both response from the TMS timing. And then we use these regressors to model the functional MRI signal from the left DLPFC region of the brain. And then we want to know that which phase being generated the largest response and which phase being generated the smallest response. And we name it the phase being that generated the largest response at the left DLPFC as the preferred phase for that subject. And the phase being that generated the lowest response, we called it as the non-preferred phase being for that subject. And then to investigate the TMS-induced functional connectivity changes, we performed the same psychophysiological interaction analysis, but here we modeled the interaction between the both signal and the timing of the TMS for each phase being. So here for the results section, I'm showing the results from the PPI analysis. And from this figure, we know that the TMS induced significantly negative effects on the functional connectivities between the deformal network and the control networks, and which is consistent with the reported literatures. And here we used the FDR at the multiple comparison correction, and we observed no significant effects on the positive side. And for the results, we also did the hub analysis because we want to know that which region in the brain that's going to be important for the propagation of the TMS effects across the brain network systems. So that we quantified the negative and the positive hubs based on the negative and the positive connections from the PPI analysis. And as shown here, that it seems that the negative hubs, they are within the control and the deformal networks, and for the positive hubs, they are in the control and the sensory networks. And then for the brain state dependency analysis, we showed that only for the preferred phase being that the TMS trials induced the significant changes across the brain networks. Where for the non-preferred phase beings, there's no significant functional connectivity changes were observed. So in conclusion, from the PPI analysis, we know that the TMS induced the strong negative effects within and between the deformal network and the control networks. And from the hub analysis, we know that the positive and negative effects of the TMS seems they follow distinct pathways. And we hope that in general that this kind of brain state dependent analysis it can be used to temporarily optimize the TMS for better treatment of depression. Thank you for listening.